The next configuration we're going to look at is an infinite sheet of charge. So I've got sort of an excerpt of this infinite sheet of charge here, and so we're saying it's going to extend in all four directions. And so I've got it sort of angled, so we're looking at the top of it, and the bottom is sort of facing away into the page. And so with this infinite sheet of charge, if we want to determine an equation for the electric field, let's consider some observation point P. So let's say we have some point P, and this point P is above our sheet, and maybe it is normal to the surface like this. And so we want to find our E at P. So consider our electric field at point P. So let's consider some differential surface charges of this infinite sheet. So let's say we have one differential part of this infinite surface charge over here. So let's call this piece 1. And then we have some other part which is equidistant from where sort of P is above that sheet. And let's call this piece 2. And so what we could know, if we're, from what we've already looked at before, just thinking of almost these DS's as little point charges, we could see that our field from 1 is going to be pushing up and to the right. So from 1, we're going to have something that looks like this. So this is due to 1. Now from 2, we're going to have an E field that's pushing up and to the left. So I say pushing very loosely. Of course, we would have to have an actual charge at P to experience a force. So the force on a charge at P would be experienced in this direction, or our electric field is directed in this direction. And so the force from 2, as I've drawn there, is going to be up and to the left. And so what we can see is that the horizontal components for 1 and 2 would cancel each other out. So let me come down here and write this. So horizontal components, or we don't even necessarily need to say horizontal components, but let me be more general and let's say non-normal components are going to cancel out. So non-normal components of our little patches 1 and 2 will cancel each other out. And so now what we can do is we can sort of do a thought experiment and say, well, really this infinite sheet is just made up of a bunch of these little differential patches. So for every differential patch, so say we put one right here, or we think about one being right here, there's going to be a corresponding one that's going to be oriented such that the non-normal parts are canceling out. So ultimately, our overall expression for E at P is only going to be normal to the surface. So let me just briefly write that. So we can say each ds has a corresponding charge patch that cancels out the non-normal component of E. And so what that's telling us is if we were to consider the charge patches from everywhere on the surface, you know, the individual ones are going to be indicated by those blue arrows there, but if we sort of sum all of them, what we're going to end up with is just one single E field line that's pointing directly away from our infinite sheet. So we're not going to go through the details of sort of the rigorous definition of this. If you would like to see that full derivation, you can look on pages 122 to 123 in the textbook, but I'll just write the result here. So it turns out that our electric field due to an infinite sheet is given by electric field is equal to rho s, which remember is our charge density on the sheet, divided by 2 epsilon naught in our un direction. And so this un direction is just the normal, so un is perpendicular to our sheet. So a very interesting thing to note about this equation is that there's no dependence on distance from the sheet. So no dependence on distance from sheet. And so that seems like a very counterintuitive thing. Again, if you're curious to see the full derivation, you can look at that in the textbook, but it's just sort of how it comes out in the math. Now, of course, physically we don't have an infinite sheet of charge, but it's sort of similar to what we talked about with our infinite line charge. There are certain cases where we can make approximations such that this equation will be appropriate. So for instance, if our point P is really close to a sheet, such that the sheet essentially looks infinite, then we can use this equation to get a good approximation.